talking about section 5.7, which is the binomial theorem. So I kind of wrote down what the theorem is, and we looked at some small examples. Let me write down the statement again. So what it says is that if I take x plus y to the power n, and if you expand this and you collect the terms, it's equal to n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the 1, n choose 2, x to the n minus 2, y to the y squared, plus dot, dot, dot. So basically, we just keep, this pattern just continues. Then you have n choose 3, x to the n minus 3, y to the power 3, and so on. And your last two terms look like n choose n minus 1, x to the 1, y to the n minus 1, and then n choose n, x to the 0, y to the n. Note that when you take something to the power 0, it's not equal to 0, it's equal to 1. It's an easy mistake to make. Okay. So this is, known as the binomial theorem. It's called binomial because this is like if you have kind of two terms like this, x plus y, you can think of that as, you can call that a binomial. And then we take a binomial to the power n, and when you expand it, this, these coefficients show up. For this reason, because of the binomial theorem, the numbers, n choose r is often called a binomial coefficient. So if you hear people talk about binomial coefficients, they're talking about n choose r. The reason it's called a binomial coefficient is because literally, in the binomial theorem, those are the coefficients, right? The coefficients look like n choose r for different values of r. So this is just a bit of terminology. When you hear binomial coefficient, it means n choose r for some n and r. Okay, so this is not like a course where we do a lot of formal proofs, but maybe I'll give you a little bit of a reasoning for this, why this theorem is true. We kind of went through a few examples to get an idea of why it was true last time, but just to kind of, just to get a rough idea of why it's true. This, by the way, the proving that this is true is not really a part of this course, so don't worry too much about it. The important thing is knowing how to use this formula. But just for your kind of interest's sake, if we want to know why it is true, it's basically, so the reason is when you expand x plus y to the n, if you don't collect, like normally when you expand things, your first instinct is to collect up all the common, all the different common factors and common terms and collect things up. But if you expand and don't collect anything, And don't reorganize anything or anything, you know. So don't collect any factors or terms. So what I mean is, you know, if, let's say you're doing x plus y squared, if you just leave it as x times x plus x times y plus y times x plus y times y. So this is what I mean by, like, don't write this as x squared and, you know, don't collect anything, just leave it out how it is. Then if you think about it, the terms that you get end up being, so the terms that you get, they will be the words, you know, all the words of length n from alpha, you know, using x, y as the alphabet. And we can see that here. This is a very simple example, but if n is 2, here I've got all the two-letter words that use the letters x and y, right? I've got, it could be xx, it could be xy, yx, or yy. Those are all the words of length 2. And each of them appears exactly once. So then you just notice that, so how many, so the coefficient, when you do collect everything, the coefficient of, let's say, x to the you know, n minus r, y to the r, should be equal to the number of words of length n that have exactly r y's. But that's the same as just taking n positions and choosing r of them to be y's. So this is equal to the number of words of length n with r y's. So it's, again, it's words just using x and y as the letters, which is equal to n choose r. So this is, when I say coefficient, I mean once you collect everything, that should be the coefficient of this. And so, yeah. And so this makes sense that when I have a 2 here, I've got a 2 here, right? It's n choose r is the coefficient of x to the m minus r, y to the r. Okay, so that's somewhat of a proof of this theorem. Any questions about that? So you don't necessarily need to remember all of this reasoning for why it's true, but knowing this is important. Yeah. Yeah. Exactly, yeah. Okay, so let's see some examples to show how to use this. So one example could be, you know, a problem you could get is simply to expand x plus y to the 6. Okay. So by the binomial theorem, we know that this is going to be 6 choose 0, x to the 6, y to the 0, plus 6 choose 1, x to the 5, y to the 1, 6 choose 2, x to the 4, y squared, six choose 3, x cubed, y cubed, 6 choose 4, x squared, y to the 4. This gets a bit tedious, but And you can work out what these coefficients are as well. So like, so this is going to give you, if I compute all these numbers, I've got x to the 6 plus 6, x to the 5, y, plus 15, x to the 4, y squared, plus 20, x cubed, y cubed, plus 15, x squared, y to the 4, plus 6, x, y to the 5, plus y to the 6. Okay. So these are things, yeah, when you plug these things in your calculator, you'll see that you get these values. Okay. Yeah. I've just got these ones memorized. There's not a really good way to calculate it. Yeah, if you ask me what is 9 choose 4, I have no idea. So, but yeah. In my research, I deal with, I do combinatorics, which is basically counting problems, and I deal with binomial coefficients all the time. So up to 6, I kind of know them all, but after that, I have no idea. Any other questions? Yeah. Well, yeah. So it is in there. So what this is saying is that basically you do n choose 0, and you do this all the way like through all the different values of this from 0 up to n. So that is here. Like your n choose n minus 1 term would be this one, because that's like your n. That's n minus 1. So you just go through all the different kind of bases here or whatever. Yeah, it's just with the dot, dot, dots and stuff, maybe it's a bit confusing, but any other questions? Yeah. Maybe on the test it'll be clarified. So if it's not clear, then either of these would have to be acceptable because there's nothing wrong with this. There's not, but yeah. So it might say like write it in a form that doesn't have any n choose r's in it or something, or yeah. Okay. So let's look at more examples. So here's a little bit of a trickier one. So, okay, well, actually, no, sorry, let's do an easy one first. So, and then we'll do a trickier one. So determine the coefficient of x to the 20, y to the 42 in the expansion of x plus y to the 62. Okay. So this one, if you kind of understand the binomial theorem, just what it says, this one should be pretty easy. But any thoughts about it? Yeah. Yeah. And then I have no idea what that is. Yeah, I didn't compute it, but it's something, right? So is it clear where this came from? So, basically, if you have x to some power, y to some power, the coefficient, well, if those, one thing you have to be careful of is that those powers need to add up to n. Here, n is 62. And these powers do add up to n. It's 20 plus 42, so this problem makes sense. And yeah, your coefficient would just be n, choose whatever the exponent of y is, which is 42. A really sneaky trick question would be Like what if this had the same, it's basically the same question, but you're asking for it in the expansion of x plus y to the 70. It doesn't really make sense. So then you would just have to say the coefficient is 0 would be your answer here. So that would be your answer here. That's simply because when I expand this, the exponent of x and the exponent of y, for every term in this, those exponents should add up to 70. These exponents add up to 62. So this thing simply cannot appear in the expansion. So you can think of it as it appears with a coefficient of 0, right? Because it doesn't appear. That is a sneaky kind of trick question. Okay, is that clear or any questions about that? Okay, let's do a little bit of a trickier one. So what is the coefficient of x to the 4 y squared in the expansion of x plus 3y to the 6? So the thing that makes this a bit different is that I've got a 3 in there, right? So, so here's a way you can kind of think of this. I mean, there's lots of different ways you can do this. You can, I mean, it is kind of possible at this point to just, if you really know what's going on, you can possibly just jump to the answer. But let's do it in a slower way, a more step-by-step way. So let's say I just let w be equal to 3y. So then x plus 3y to the 6 is x plus w to the 6, right? Because I can substitute w in for 3y. So in here, the coefficient, well, so the expansion of this contains the term, so it'll contain a term that looks like 6 choose 2 x to the 4 w squared. Right, because this is just by the binomial theorem. Just being, so this is, this is just called w, but it doesn't really matter what you call the variable, right? So when you expand that, it'll have a term that looks like this. And then you can just say, well, I remember that w is equal to 3y. So that's the same as 6 choose 2 x to the 4 3y squared, which, so the square goes kind of inside here. So it's 6 choose 2, 3 squared, x to the 4 y squared. And so then this is your coefficient. 6 choose 2 times 3 squared. So 15 times 9, I think. which would be 135, I think. Yeah. Well, the question asks for x to the 4 y squared. But if it asked for x cubed, y cubed, you could do exactly the same thing. And here you'd look at the term that's like x cubed, w cubed, and this would be a 6 choose 3. And then it would be like 20, the answer would be 27 times 6 choose 3 would be your, the 27 comes from 3 cubed. But yeah, it would be exactly the same process. So I only looked at that term just because this was what it was asking for. So it wants a term that has an x to the 4 in it. So I better take the term that has an x to the 4 in it, or else you're not going to have that, right? Any questions about that? Okay, and you can have all kinds of variations of this. This could have been, 4x minus 3y to the 6. It could have been all different things, but as long as you kind of substitute things correctly, remember how to use powers, like the fact that this squared goes on the 3 and on the y. Basically, if you know your rules of arithmetic, you're good at substituting things, it shouldn't be too bad. Okay. Let me now tell you another nice thing about the binomial theorem. It allows you to derive some cool formulas. Well, I mean, arguably cool. So basically, using the binomial theorem, we can get interesting formulas by plugging in values for x and y. So for example, what if we plug in x equals y equals 1? So the left side is going to be 1 plus 1 to the power n, so it's 2 to the n. So the first term here, well, actually, if you think of all the terms, like if I plug in a 1 for x, 1 to the power of anything is 1, right? So this is just a 1, that's a 1. All these terms are just like binomial coefficients times 1 times 1. So that tells us that 2 to the n is equal to n choose 0 plus n choose 1 plus n choose 2 plus dot, dot, dot. All the way to n choose n. Right. Another kind of interesting one is, what if I plug in x equals 1 and y equals negative 1? Yep. How do I get the 2 to the n? That's plugging in on this side of the equation. So just 1 plus 1 to the n. Yeah. So now if we plug in x equals 1, y equals negative 1. So in this case, what is my left-hand side going to equal? Yeah, it's 0 to the power n, so it's 0. And then on the right side, we get something kind of interesting. So the first term, so it's 1 to the n, negative 1 to the 0. Anything to the power 0 is 1, except for arguably 0, but let's not worry about that. So this would be n to the 0, or sorry, n choose 0. The next term, I've got a 1 here. I've got a negative 1, because negative 1 to the 1. Basically, negative 1 to an odd power is negative 1. To an even power, it's 1, right? Negative 1 squared is 1. So my next term is minus n choose 1. I get plus n choose 0, minus n choose 3, plus dot, dot, dot. The last term is not so clear. It depends on, it'll either be a plus or a minus, depending on if n is even or odd. But yeah, so this gives you that, like kind of magically, if I add up all my binomial coefficients, but with alternating signs, plus, minus, plus, minus, plus, minus, for every value of n, this always equals 0. Okay. And you can have fun playing with that, put in different values for x and y and see what happens. Yep. So this is, so here you would have x to the n, y to the 0, which is like 1 to the n, negative 1 to the 0, which would be 1. On that term, you would have 1 to the n minus 1, negative 1 to the 1, which then makes a negative 1. And if you think about it, for each term, the x part of it is always giving you a 1, because it's 1 to some power. The y term, or the y factor here, when it's an even number, like 2, it gives you negative 1 squared. It's 1. When it's odd, like say negative 1 cubed would give you negative 1. And it just kind of switches back and forth like that. Yeah, yeah. So sorry, could you? I mean, yeah, if you plugged in, or for example, now just times both sides by negative 1. If the equation's still true, and then you'd have negative here, plus here, negative here, plus there. Yeah. That's probably the easiest way to see it. Any other questions? Okay, so for the last, I don't know, 18 minutes or so, we're actually going to move on now to the next chapter, which is probability. Okay, so chapter 6. Okay. Okay, I can't remember exactly what this section's called, but it's something like sample spaces, experiments, and stuff like that. So let me just sort of give you a rough idea of how, how to get started talking about probability. So when you're doing probability, often you think of it as doing an experiment and getting an outcome. And you want to know, like, what's the likelihood of each possible outcome? So like, you could flip a coin. Your possible outcomes are heads or tails. Each of them should have 50% probability, right? And flipping the coin in that case would be your experiment. So just kind of vaguely speaking, an experiment is an activity like flipping a coin with an observable outcome. And then the set of possible outcomes for an experiment is called the sample space. Okay. And you might remember when we did set theory, we had this letter U that was always used for the universe. And here we're going to have the letter S is always going to be the sample space. So, or usually anyway. So we usually use the letter S to denote the sample space. Yeah. Yeah, not quite. So the question was, yeah, I think the section title maybe has the word events in it. Events are not the same as experiments. There's a question whether, I mean, they both start with the letter E, so you might, but yeah, no, we'll define what an event is in a minute. Okay, so as an example, an experiment could be, well, I already said one, like flipping a coin, right? Another example is, you know, roll a die and observe the outcome. So this would be an experiment. So in this case, what would be my sample space? Yeah, so exactly, yeah. So yeah, the sample space will always be a set, and the set like consists of the possible outcomes. So these are the possible outcomes for rolling a six-sided die, right? Now, an event is a subset of the sample space. So notice an event isn't necessarily, it's not like necessarily just one outcome or something, right? An event can be any subset of the sample space. So for example, if I take E to be the set 2, 4, 6, you know, so this is the event that an even number is rolled. So this is, so E, like, this is the way to write it in set theory notation. But if you wanted to explain what does E represent in words, well, in words, E is the event that that an even number is rolled, right? And the point is, it's a subset of S, meaning every element of E is an element of S, right? You can't just, I couldn't say E is the set 2, 4, 6, 7, because like 7 is not a possibility for this experiment, right? So I wouldn't include 7 in my event. So if the outcome, if you do the experiment, if it happens to be an element of an event E, we say that the event E occurred. Okay. So if I say, suppose I do this experiment, what's the probability that E occurs? Well, in this case, it'd be 50%, right? If it's not a weighted dice or die or something, right? So what it means for E to occur means that the number is even. Okay. So note that this definition of event does give you some strange possibilities. Like, for example, the empty set. Well, the empty set is a subset of every set. So technically, this is an event. But the thing is, it's not possible for that event to occur, right? So it's an event that can never occur. So it's like, we might call it the impossible event. And also, the set S itself, the sample space, is also an event. But this is a bit different because the event S always occurs, right? If you think about it, if I roll a die, one of these things always happens. Like it's always 1 or up to 6, unless somehow the die, if it balances on a corner or something, but that's not very likely, right? So S is the event which always occurs. It's sometimes called the certain event. Any questions about this? Okay. All right, so let's get a little bit more familiar with these concepts. So let's say that you have a bin. It contains 10 white balls and 10 red balls. And suppose that you pick out three balls from the bin at random, one at a time. So you pick one out, maybe you put it back. In this case, it's not going to matter, but pick out 3 balls from the bin, one at a time, and observe the sequence of colors that you see. So there's going to be 3 different colors, 3 different balls, right? Or, yeah, not different. Yeah, you're always going to have the same one twice at least. But so what would be the sample space for this experiment. Okay. Well, that's kind of a natural choice, right? Because but if I was just picking one ball, then definitely red and white are the only two options. Here though, my experiment is a bit longer. My experiment has actually three. So yeah, your experiment can be kind of 3 experiments in a row, which this one is. And so you're going to have a bit of a bigger sample space because it could be, so basically it could be red, 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 white, red, white, red, red, white, 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 red, red, white, red, white, 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 red. I kind of think I'm, sorry. Yeah. Or white, white, white. Right, so the letters just represent the 2 colors. So yeah, your experiment is picking 3 balls, and these are all the possibilities you could have, right? So in particular, the number of elements of your sample space is 8. If you count them up, you'll see that there's 8. Okay, so now let's, oh yeah? Yeah, in this case, you could also, if you were asked just for the number rather than writing them out, you can kind of figure out how many there are because, you know, there's 2 possibilities for the first choice, 2 for the second, 2 for the third. So it should be 2 times 2 times 2. So it should be 8 for that reason. So if you were asked to just find out how big is the sample space, you could just write, you know, it's 2 times 2 times 2, which is 8, and you wouldn't have to go through all of this. Yeah. Yeah, so there'd just be a couple more 2s because, you know, for the first ball, you've got 2 options of the color. Second one, 2 options for the color. And yeah, so that many possibilities in total. Okay, so here's another question you could be asked. So let E be the event that exactly one red ball is chosen. List the elements of the event E. Okay. So here, so you need to be able to translate between kind of writing events in words and then writing them in set theory notation. So that's what this is asking you to do. We've described the event in words. It's the event that exactly one red ball is chosen. Now you need to translate that into set theory. Right? And basically, you can just go through your sample space and pick out the ones that have the property, right? So this one has exactly one red ball. So RWW. It could be WRW or WWR. Okay. Okay, so just quickly now, one more question you could be asked, like, so let F be the event that the first ball is red, Now, you could be asked to describe the set E intersect F in words. Or when I say set, I mean event. So describe the event E intersect F in words. Yep. There'll be some probability on it. There's going to be at least a couple of sections, maybe 2 or 3 sections of this. Yep. October the 4th, I think. Okay. But, okay, for the next 30 seconds, let's focus on this question. And does anyone have a way of describing this in words? Yep. Almost, yeah, yeah. Yeah, exactly, yeah. So this is an intersection. This is the event that there's exactly one red ball, and the first ball is red. So actually, it's just going to be the probability the first one's red, the other two are white. Or the event that happens.